In a previous video, we learned about what inverter ride-throughs are. Well, in this video, we're going to go over an example of what some requirements could look like and how to specify the inverter settings in order to meet it. All right, let's get started. Let's go over an example requirement for voltage ride-throughs. Here is an example standard for ride-through general requirements. This is telling us what inverters should be able to accommodate under this standard. Utilities may choose to use this or create their own standard. For this, let's assume the utility is using this standard. In my examples earlier, really just focused on the voltage dropping and the inverter responding to that. However, the inverters are to ride through voltage swings high and low, and you can see that here in this example requirements. On the left, we have voltage in PU, and that is per unit. And if you multiply that by 100, you just get percent. The x-axis is time in seconds in the logarithmic scale. And there is a key here that shows you what each response means. Let's go over that now. First is must trip. Inverters trip, electrically remove itself from the circuit by opening up its contactors, and then it has to wait 5 minutes before it can try to reconnect. Next is cease to energize. Now this does not trip. It just sets its power output to 0 and hopes that the grid event recovers before it must trip. Normal operation. This is just normal voltage range, so it may continue to operate as intended. And last is must continue to operate. So although there is an event, the inverter is to continue to operate as normal as to attempt to support the grid through the event. So if you have voltages that are between 1.1 and 0.88 of nominal voltage, this is considered normal and the inverter is to run normally. That's this green area. Now if the voltage were to go above 1.1 up to 1.2, and again that could be interpreted as 110% to 120% of nominal, then the inverter is to momentarily cease to operate for at least 12 seconds. In general, exporting power to the grid contributes to pushing the voltage up. So it makes sense that they would want the inverter to not export power during this time when the voltage is already too high. The inverter must trip by 13 seconds. So between 12 seconds and 13 seconds, the inverter may continue to wait or trip. It's kind of a quote-unquote gray area. Now, if the voltage were to recover within the 13 seconds, then it would not trip and continue to run as normal. If it does not recover, then it will trip offline, and then it will need to wait at least 5 minutes until it can try to reconnect. From 1.2 and above, the inverter must trip by 0.16 seconds. There is no minimum requirement to operate, so this is another quote-unquote gray area, and it is saying that you may continue to run or you may trip. This is the same may trip area in the earlier example. It's just a little hard to see between 12 seconds and 13 seconds. It's flexible on when you trip as long as you trip by 0.16 seconds. Now let's take a look at when the voltage drops below nominal. So from 0.88 to 0.7, the inverter must continue to operate as normal for at least 20 seconds. And then from 0.7 to 0.5, it must continue to operate for at least 10 seconds. Like I mentioned before, exporting power contributes to a higher grid voltage. So if the voltage is dropped, it makes sense that the utility would want the inverters to continue to run and help hold the voltage as high as it can to try to prevent a collapse. However, if the voltage sags long enough, both of those sections must trip by 21 seconds. So this region between 0.7 and 0.5, it may trip or may continue to operate between 10 seconds and 21 seconds. Lastly, below 0.5, the inverters must cease to energize for at least 1 second, and then it must trip by 2 seconds. There's a little wiggle room on what it could do between 1 second and 2 seconds, and that again is a may trip area. Now that we went over the requirements, let's take a look at 2 example settings that are slightly different. Here is one example of settings that will meet the standard requirements. We have 0.16 seconds, 13 seconds, 21 seconds, and 2-second trip points at these corresponding voltages. The 21 seconds basically covers the entire 0.88 to 0.5 and fills in that may trip area into a rectangle. This one setting covers this entire voltage range. Here is another example, and everything is the same, but the 0.7 to 0.5 range has different settings of 11 seconds. This introduces an additional undervoltage setting for a total of 3 undervoltage set points. These are just 2 examples on how you can meet the standard requirements with 2 different set points. We just talked about voltage ride-throughs, but the same concept can be applied to frequency ride-throughs. Modern PV inverters have the ability to ride through faults and support the grid in many different ways through events in order to promote grid stability. Their impact extends beyond individual PV systems, benefiting the entire utility sector. If you want to learn more about another grid support function, go ahead and put it in the comments below. Thank you for joining.